Trig Substitution Part 1. Consider these three integrals on the screen. We should know the antiderivatives for each one of these. The first one is an arcsine. The second one is an arctangent. But the arctangent has an extra 1 over a out front. That's not really the important part. We're just doing these correctly. And the third one is an arcsecant, which also has an extra 1 over a out front, and the plus our constant of integration. So we're going to look at integrals that are very similar to these three, but that take a different integration technique. Let's start by considering integrals that look like dx over root 1 minus x squared, which is an arcsine of x. And I want you to focus on the sine. We'll get back to that in just a little bit. Let's start with integrals we already know how to do. That look very similar. This is not an arcsine at all. In fact, the technique is integration by substitution, or what we usually call U sub. What if I have another one that looks like the original, but without the square root? Well, this one I would consider doing partial fractions. But what if we have one of this form? Instead of 1 minus x squared to the 1/2 in the denominator, what if it's to the 3/2 power? So a problem like this is not U substitution. It would be if there's an x up top. It's not partial fractions, it's not integration by parts, really it's not anything else we know. So we're going to try a technique called trig substitution. And what we have to recognize is that this integral looks pretty similar to this integral up top, which is an arcsine. This tells me we're going to do a trig substitution of the following fashion. Let's start by drawing a right triangle. And we'll get an angle theta somewhere. Let's put it right here in the bottom right. There's the right angle. And my claim is that we should do the following substitution. I'm going to let sine of theta equal x. Or more specifically, x over 1. Now, why did I choose to do this? Well, first of all, it looks like an arcsine. I have an x over a if you're used to the notation that we have up top. That's where I get the x over 1. But the real clue comes when we fill in our right triangle. So if I choose sine of theta to be x over 1, then x is the opposite side to the angle, and 1 is the hypotenuse. And by Pythagorean theorem, we can get the third side, which is root 1 minus x squared. So what we want to do now is substitute everything that has an x in this integral for something with a theta. Let's start with dx. If x is sine theta, then dx is cosine theta d theta. All right, that's taken care of. Now let's look at the denominator. Going back to our right triangle, we see that the cosine of theta equals root 1 minus x squared, or root 1 minus x squared over 1, because cosine is adjacent over hypotenuse. That means that if I cube this, I get the denominator, which means I need to cube the left side as well. And then we can substitute in. So dx is cosine of theta d theta. The denominator is cosine cubed of theta. And we'll simplify. We get d theta over cosine squared of theta, which I'm going to rewrite one more time as secant squared theta d theta. Because we should know the antiderivative of secant squared, which is tangent of theta, plus c, of course. But just like with u substitution, when we should go back to x's, with trig substitution, we should also go back to x's. And we can go back to our right triangle and find the tangent of theta. Well, the tangent is opposite over adjacent. And that gives us the antiderivative.